Dear students, in previous class we discussed about the grouping of series and rearrangement of series. What is grouping? Is if sigma xn is any given series, then sigma yk is obtained from the sigma xn by keeping the element fixed in sigma xn and inserting some brackets. And what about rearrangement? The rearrangement series is obtained from the given series by using all the terms of the given series exactly once and scrambling the order. Also we say that when the rearrangement theorem, that's an important result. The theorem states that sigma xn is absolutely convergent. Then every rearrangement series sigma yk is also absolutely or also converges to the same value. That is rearrangement theorem. Okay. Now consider a result. If sigma an is conditionally converges, consider a series sigma an which is conditionally convergent. Then the series is obtained from its positive terms and the negative terms are divergent. Rearrangement theorem that is deals about the absolute convergency, but here the theorem states that when a series is not absolutely but it is conditionally convergent, then the series obtained from the positive terms as well as its negative terms are divergent. So far, how to prove this one? Its proof is, let S equals sigma A. That is conditionally convergent. Let S plus equals sigma an plus. That is the series obtained from positive terms. And S minus equals sigma an minus. That is the series obtained from negative terms. So, now to prove S plus and S minus are divergent. That is what we recurse here. Agree. But we have, what is an plus? We know that an plus equals, it is an plus modulus of an divided by 2. And what is an minus? An minus equals an minus modulus of an divided by 2. Okay. If possible, S plus converges. What happens? We prove that our requirement is S plus diverges if we suppose S plus converges. S plus converges means, let S plus converges. From here what is an? From this result, what about mod an? Here mod an equals 2 into an plus minus an. Agreed. Take summation on both sides, that is sigma mod an equals, that gives sigma mod an equals 2 into sigma an plus minus sigma an. But our assumption is S plus converges. What is S plus? Sigma an plus. So sigma an plus converges. Sigma an, that is also converges. That is given. So what about the right side? Right side is converges. That gives sigma mod an converges, which is a contradiction to the given assumption. Given hypothesis. Why? It is given sigma an is conditionally convergent. It's clear that sigma mod an diverges. Okay, so that's a contradiction. This contradiction is due to this assumption. Therefore, S plus not converges means it diverges. Similarly, you can prove that S minus is also diverges. If S minus converges, what happens? If S minus converges, what happens? What is from here? From this result, what is mod an? Here also mod an equals 2 into an minus an. Again, if we take sigma on both sides, sigma mod an equals 2 sigma an minus sigma an. By assumption, sigma an minus converges. Hypothesis, sigma an converges. So sigma mod an converges. That's again a contradiction to the hypothesis. So the rearrangement series or the positive and negative terms of the series which includes positive and negative terms of a given conditionally convergent series, the series may be diverges. Okay, right. Then come to the next result. That's an important one. Here, if sigma an is absolutely convergent, sigma an absolutely convergent. If sigma an is absolutely convergent, then every rearrangement of sigma n is also absolutely convergent. What is rearrangement theorem? Rearrangement theorem states that when a series is absolutely convergent, then the rearrangement of sigma y, okay, that converges to the, or rearrangement of sigma xn converges to the same value where sigma xn converges. Here we say that when sigma an absolutely convergent, then we try to prove that sigma an, every rearrangement of sigma an is absolutely convergent. How? So for let sigma an dash or sigma bn, whatever, sigma an dash be a arbitrary rearrangement of sigma a. Then sigma an dash be an arbitrary rearrangement of sigma an means sigma mod an dash be an arbitrary rearrangement of sigma mod a. Sure? Okay. What is sigma an? But sigma an is absolutely convergent means sigma mod an converges. Sigma mod an converges. So sigma mod an converges means sigma an is absolutely converges. Therefore, by rearrangement theorem, sigma an dash converges. Sigma an dash also converges. What is rearrangement theorem? When sigma an is absolutely convergent, then the rearrangement of the sigma an converges to the same value to which sigma an converges. So, sigma an dash be an arbitrary rearrangement of sigma an, then sigma an dash is arbitrary rearrangement of sigma an, but what is sigma an absolutely converges. So, by that rearrangement theorem, sigma an dash converges to the same value at which sigma an converges. So sigma an dash converges. Okay. Again, sigma an absolutely convergent means sigma mod an is also absolutely convergent. Sigma an absolutely convergent means sigma mod n is also absolutely convergent. Why? Because modulus of mod an is also mod an. Okay? Modulus of mod an is also mod an. So when sigma an absolutely converges, then sigma mod an converges. When sigma an absolutely converges, then sigma mod an also absolutely converges. Okay. So, but what is sigma mod an dash? Sigma mod an dash is an arbitrary rearrangement of sigma an. Then again by rearrangement theorem, when sigma mod an absolutely converges, sigma mod an dash also absolutely converges. Clear? Sigma mod an dash also converges. Sigma mod an dash converges means sigma an dash is absolutely convergent. Get it? Sigma an is arbitrary, absolutely convergent. Sigma an dash is an arbitrary rearrangement of sigma mod an. So, but sigma mod an converges. Why? Because of the absolute convergency of sigma an. Sigma mod an converges by rearrangement theorem, sigma an dash converges. But sigma mod an converges means sigma mod an is absolutely convergent. Why? Because this one, modulus of mod an is mod an. Okay. So sigma mod an absolutely convergent and sigma mod an dash is an arbitrary rearrangement of sigma an. Then again by rearrangement theorem, sigma mod an dash is converges. Sigma mod an dash is converges means sigma an dash is absolutely converges. Get it? Okay. Now let's suppose sigma an is absolutely converges. Consider another one. Let sigma an absolutely converges. sigma an absolutely converges. Bn be a bounded sequence. Sequence Bn is bounded. What about the series sigma an Bn? Is it absolutely or conditionally converges? Sigma an absolutely converges. Bn is a bounded sequence. Sequence Bn is bounded. Then what about the series sigma an Bn? Is it absolutely or conditionally converges? So, see, consider sigma an absolutely converges means sigma mod an converges. Okay, this implies sigma mod an converges. Bn bounded means there exists m greater than 0 such that mod Bn strictly less than or equals m. Mod Bn less than or equals m for all m. Okay, right. So what about modulus of a and bn? Mod a and bn equals mod an into mod bn, which is less than or equals mod bn means m into mod a. Okay, right. Therefore, sigma modulus of a and bn less than or equals sigma m into mod a, that equals m into sigma mod a. Now listen, what is sigma mod a? Sigma an absolutely convergence means sigma mod an converges. Okay, so sigma mod an given sigma mod an converges. Sigma mod an converges since m is a positive real, therefore m into sigma an is also converges. That means sigma mod an bn less than or equals m into sigma mod an converges. So by comparison test, right side sigma mod an, m sigma mod an converges. Therefore by comparison test, sigma mod an bn converges. Sigma mod an bn converges means what is sigma an bn? Sigma an bn is absolutely converges. So that's the conclusion. When sigma an is absolutely converges and bn is a bounded sequence, then sigma an bn is also absolutely converges. Agreed? Okay. Now, again, consider a series sigma an. If sigma an is conditionally converges, sigma an is conditionally converges. If sigma an is conditionally converges and bn is bounded, bn bounded, what about sigma a and bn again? Is it conditionally or absolutely converges or diverges? Check the convergency or divergency of sigma a and bn. Previous example or previous argument shows that when sigma an is absolutely convergent and bn is bounded, then sigma a and bn is also absolutely converges. Here, check the convergency or divergency of the series sigma a and bn, where sigma an is only conditionally converges, not absolutely, only conditionally converges. Moreover, bn is bounded. How? So, consider, let sigma an equals, consider a series, sigma an equals minus 1 power n by n, minus sigma an equals or an equals, consider an equals the nth term of a series, so sigma an equals sigma minus 1 power n by n. Surely it is conditionally converges. Why? Because what is sigma mod n here? Sigma mod n is sigma modulus of minus 1 power n means 1 itself. So it is sigma 1 by n, sigma 1 by n diverges. Okay. So sigma n is a conditionally convergent series. And let Bn equals minus 1 power n. Surely Bn is bounded. What about mod Bn? Mod Bn less than or equals 1. It is bounded by 1. Okay, mod Bn is 1. Bounded by 1. So clearly Bn is a bounded sequence and the sigma an is conditionally converges. What is sigma an Bn here? Sigma an Bn equals sigma, what is an? Minus 1 power n by n into what is Bn? Minus 1 power n. That equals sigma minus 1 power 2n. That is minus 1 power 2n means 1. So it is sigma 1 by n. What is sigma 1 by n? Sigma 1 by n is a harmonic series and we say that it is divergence. So sigma a and bn is always divergence. Here not always, it may divergence. So that is another result. When sigma an is conditionally convergent and bn bounded, then sigma an may diverge. Need not be converges. But if sigma an is absolutely converges, and bn is bounded, then sigma a and bn is also absolutely converges. But if sigma n is conditionally converges and bn is bounded, then sigma a and bn may diverge. Enough. Now consider the test for absolute convergence. Test for absolute convergence. What is it? We already studied about the test for convergence. Which are the tests for convergence? Comparison test, nth term test, and limit comparison test. Okay, we already studied about three convergence tests. That is the test for convergence, nth term test, limit comparison test, as well as comparison test. So here we also discuss about the different types of absolute convergence test or test for absolute convergence. The first one is limit comparison test. Limit comparison test is same that of the limit comparison test which is used for testing the convergence of a series. So what is the limit comparison test here? Suppose that x equals xn and y equals yn are any two non-zero real sequences, and r equals, if sequence x equals xn and y equals yn, x equals xn and y equals yn are any two sequence of non-zero terms or non-zero real sequences, such that r equals limit xn by yn. R equals limit xn by yn exists. Then if r differs from 0, then sigma xn is absolutely converges implies sigma xn absolutely converges if and only if sigma yn absolutely converges. Okay. If r equals 0, then sigma yn absolutely converges if and only if sigma xn absolutely converges. So this is limit comparison test. Proof is same as that of the limit comparison test for testing the convergence of a series. So this is the first test, limit comparison test. So it is known as second limit comparison test. That this test is used for testing the absolute convergence of a given series. So the proof is immediate. This proof is same as that of limit comparison test, which we already discussed. Now the second one is, come to the second test. The second test is root test. Root test. What is root test? Second test is root test. What is root test? Let xn is a sequence in R. Let sequence xn be any sequence in R. real sequence if there exists R following R. If there exists a real number R such that modulus of with the R less than 1, R following R with R less than 1, comma, there exists a natural number K such that modulus of x power 1 by n, modulus of x power 1 by n less than or equals R for all n less than or equals R for all n greater than or equals K, K is a natural number, then the series sigma xn converges absolutely. Sigma xn converges absolutely. This is the first part. If xn is a real sequence, then there exists a real number R with R less than 1, and there exists a natural number K with a mod x power 1 by n less than or equals R for all n greater than or equals K, then sigma xn converges absolutely. Its proof is immediate. Why? We have mod x power 1 by n less than or equals R. That means modulus of x less than or equals R power n. So what is sigma mod x? Sigma mod x less than or equals sigma R power n. What is R? R lies in between 0 and 1 or R less than 1. Since R less than 1, what about sigma R power n? There is a geometric series with a common ratio less than 1, so it always converges. Therefore, that means sigma mod R power n converges. Therefore, sigma mod x converges by comparison test. Sigma mod x converges means x equals xn converges absolutely. So the proof is immediate. Its second part is, if modulus of x power 1 by n greater than or equals R, greater than or equals 1, modulus of x power 1 by n greater than or equals 1, then the series sigma xn diverges. So that's again immediate. See, mod x power 1 by n greater than or equals 1 means limit x power 1 by n differs from 0. So by nth term test, sigma xn diverges. So this is the proof of root test. Root test is an important one. So if xn is a sequence of real numbers and mod x power 1 by n less than or equals R, if R less than 1, then sigma xn converges absolutely. If mod x power 1 by n greater than or equals 1, then sigma xn diverges. Okay, right.